Hello, dear students. Glad to meet you again in this session. In this session 2.13 from chapter 2, Structure of Atom in grade 11, we are going to discuss the electronic configuration of atoms with atomic number 21 to 30. Before getting into today's concept, let us recall all the topics that we have discussed in the previous sessions. In session 1, we have discussed the discovery of subatomic particles. In session 2.2, we have discussed J.J. Thomson and Rutherford atomic model and its drawbacks. In session 2.3, we have discussed dual nature of electromagnetic radiation. In session 2.4, we have discussed atomic spectra. In session 2.5, we have discussed Bohr's atomic model. In session 2.6, we have seen two developments towards quantum mechanical model of atom. In session 2.7, we have discussed quantum mechanical model of atom. In session 2.8, we have discussed orbital and quantum numbers. In session 2.9, we have discussed shapes of orbital. In session 2.10, we have discussed energies of orbitals. In session 2.11, we have discussed filling up of orbital. In session 2.12, we have discussed the electronic configuration of first 20 atoms. Learning outcomes. Students, at the end of this session, you will be able to write the electronic configuration for the atoms with atomic number begins with 21 to 30 and describe the exceptional configuration of chromium and explain the exceptional configuration of copper. So far, we have seen the electronic configuration of first 20 elements in the periodic table, right? Now we are going to see the next 10. A new pattern is followed beginning with scandium, which is the 21st element in the periodic table. That is, it has 21 electrons in its atom. Let us see what is the new pattern of electronic configuration from scandium. Okay. Now, look at this increasing order of energy. So while writing the electronic configuration, we use this increasing order of energy according to Appá principle, right? So 1s, 2s, 2p, 3s, 3p, then the electron goes to 4s, that is the n shell. It goes to the 4s orbital in n shell, right? 4s, and we would expect that the electrons next go to the 4p orbital in the n shell, but instead it comes down to the m shell and occupies the orbitals in 3d. So this is the new pattern followed from scandium. So as usual, 1s2, 2s2, 2p6 up to this neon configuration, right? 3s2, 3p6. So totally 10 plus 12 plus 6, 18. Then 4s2, 20 we have written, right? So how many electrons actually we have in scandium? 21. So 21 minus 20 remaining, how many electron is there? Only 1. So this electron won't occupy 4p orbital, which is in n shell. Instead, it comes down to the d orbital in the m shell. So the electronic configuration of scandium is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and 3d1. Now shall we see the orbital diagram for scandium? As usual, we have to draw boxes for each and every orbital. So for 1s, we have drawn one box, 2s, another one box, 2p, degenerate orbital. So consecutively, 3 boxes because we have 2px, 2py, and 2pz. Then 3s, another box, 3p6, consecutive 3 boxes, 4s, 1 box we need to draw. Then for 3d orbitals, we have how many d orbitals? 5, right? So we need to draw 5 consecutive boxes. So 2 electrons in 1s, 2 electrons in 2s. We have to represent the electrons by upward and downward arrow mark, which represents the opposite spins in each orbital, right? So 2 electrons in 1s, 2 electrons in 2s, and 2 electrons in 2px, 2 electrons in 2py, 2 electrons in 2pz, on the whole 6 electrons. Then 3s2 we have 2 electrons, 3p6 also we have 2 electrons in each of the orbital, that is 3px, 3py, and 3pz. So totally 6 electrons we need to draw here. Out of these 6, 3 will be in the upward arrow mark and 3 will be in the downward arrow mark. Then 4s2, we have to draw 2 arrow marks, one upward and one downward as usual. Then we have how many electron? Only 1, right? So it will occupy the first orbital, that is 3D XY orbital. So we need to draw an upward arrow mark which represents the parallel spin. So this is the orbital diagram for scandium. Now let us go to titanium. Only 1 electron is more when compared to scandium, right? So the same pattern we need to follow. So 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d2, right? Why we have written 3d2? Because 2 plus 2 plus 6, 10, plus 2, 12, plus 6, 18, plus 2, 20. Up to 4s, we have completed 20 electrons. Totally, we have 22. So 22 minus 20, remaining 2 electrons will be there. That 2 electrons will occupy 3D orbitals. So shall we write the orbital diagram for titanium? It is same as that of scandium. So as usual, we need to fill up the electrons in the corresponding boxes up to 4s2. Then when coming to 3D orbitals, these 2 electrons won't pair up because according to Hund's rule of maximum multiplicity, pairing up of electrons takes place only when there is no empty orbital. So these 2 electrons won't pair up and occupy the 3D XY orbital. Instead, one of the electron will occupy 3D XY orbital and the last one, another one, will occupy the 3D XZ orbital. So we need to draw one upward arrow mark in 3D XY and one upward arrow mark in 3D XZ. You have to be very careful while filling up the electrons in degenerate orbitals. Coming to vanadium, we have 23 electrons because the atomic number is 23. So as usual, like scandium and titanium, we have to write the electronic configuration for vanadium in terms of scientific notation. 1s2, 2s2, 2p6 electrons we need to write because it can accommodate a maximum of 6 electrons. 3s2, 3p6, 4s2. Up to this, how many electrons shall we count? 2 plus 2 plus 6, 10, 10 plus 2, 12, 12 plus 6, 18, 18 plus 2, 20 electrons we have completed. So totally how much we have in vanadium? 23. So 23 minus 20, remaining 3 electrons we have. That 3 electrons will occupy the 3D orbitals. Now coming to orbital diagram for vanadium. As usual, from 1s to 4s, we need to complete the boxes with upward and downward arrow mark, which represents the opposite spins of electrons in each of these orbitals. Now, when we come to 3D orbitals, again, we have to remember Hund's rule of maximum multiplicity. So it won't get paired up, right? So we have how many electrons here? 3 electrons. The first electron will occupy 3dxy. The second electron will occupy 3dxz. And the third electron will occupy 3dyz, right? In these 3 orbitals, we need to draw the upward arrow mark, which represents the positive spin of the electrons. So a new pattern is followed, beginning with scandium. So here the 3D orbital being the lower energy than 4p orbital is filled first. The electronic configuration of chromium is very peculiar. So now we are going to see the exceptional electronic configuration of chromium. The actual configuration of some elements differ from the expected electronic configuration, which is in accordance with Abba principle. Chromium has 24 electrons. That is, the atomic number is 24. So it has how many electrons? 24. So what is our expected configuration? 1s2, 2s2, 2p6, 3s2, 3p6, 4s2 and 3d4, because 2 plus 2 plus 6, 10, 10 plus 2, 12, 12 plus 2, 18, 18 plus 2, 20. We have 24 for chromium. So 24 minus 20, remaining 4 we have. So we would expect the 4 electrons in 3d orbitals, right? This is the expected configuration of chromium, which is in accordance with the Abba principle. So while drawing the orbital diagram for chromium, we used to draw one box for each orbital. So one box for 1s, one box for 2s, and 3 consecutive box for 2p, and one box for 3s, and 3 consecutive box for 3p, and one box for 4s, and 5 consecutive boxes for d orbital, since it has 5 orbitals, right? So starting from 1s up to 4s, as usual, we will draw the electrons, one upward and one downward direction, which represents the opposite spins, as we have done for scandium, titanium, and vanadium. Coming to 3d orbitals, how many electrons we have? 4 electrons. So as usual, we will draw one arrow mark. The first electron will occupy the 3d xy. The second electron will occupy 3d xz. The third electron will occupy 3d yz. And the fourth electron will occupy 3d x minus y square. This is our expected configuration, right? But the actual configuration differs from the expected one. Configuration of chromium is 1s2, 2s2, 2p6, 3s2, 3p6. Instead of 4s2, only one electron occupies the 4s orbital. Instead of 3d4, 5 electrons will occupy the 5d orbitals. This is the peculiar case. The expected one is 4s2 and 3d4, right? But it is not like this. The actual configuration is 4s1 and 3d5. Electronic configuration in terms of orbital diagram for chromium, 2 electrons will occupy 1s2 as usual, 2 electrons will occupy 2s2 as usual, 2 electrons will occupy 2px, 2 electrons 2py, 2 electrons 2pz, 2 electrons occupy 3s. Coming to 3p, 2 electrons will occupy 2px, 2 electrons will occupy 2py, 2 electrons will occupy 2pz. Up to this is normal, right? Coming to 4s, we would expect 2 electrons will be there, right? But instead, only one electron will occupy the 4s orbital, and the second electron will occupy 3d orbital. In this actual configuration, each d orbital accommodate one electron, and all these electrons will have positive spins. This is the actual configuration. The reason is, when you look at this expected configuration, there is one empty box here, right? But in the actual configuration, all the orbitals are occupied by one electron, right? When you look at this orbitals of 4s and 3d, it is half filled, right? Fully filled orbitals and half filled orbitals have found to have extra stability. This is the reason chromium has a peculiar electronic configuration. This reason can be well explained on the basis of the symmetrical distribution of electrons and exchange energy, which we are going to see in the next session. Now let us see the electronic configuration of next 4 elements: manganese, iron, cobalt, and nickel. These 4 elements will follow the pattern as that of scandium, titanium, and vanadium, right? Let us write the electronic configuration in terms of scientific notation first. So to write the electronic configuration, as usual, we have to write according to the increasing order of energy in accordance with the Appel principle. So we know that 1s, we can accommodate 2 electrons. So 1s2, 2s2, 2p6 because it could accommodate 6 electrons. Then again 3s2, 3p6 up to 4s2 as usual as we have done for scandium, titanium and vanadium, right? So totally how much we have written so far? 2 plus 2 plus 6, 10 plus 2, 12, 12 plus 2, 16, 16 plus 2, 20 we have written. How much we have? 25. So 25 minus 20 remaining how much we have? 5 electrons, and these 5 electrons occupy the 3D orbital. Now shall we write the orbital diagram for manganese? So from 1s to 4s we have to draw the boxes and we have to fill the electrons as we have done for vanadium. That is 2 electrons in each box, and inside this each box, so 1 arrow mark in the upward direction and 1 arrow mark in the downward direction, which represents the opposite spins of electrons in each of these orbits, right? Coming to 3D orbitals, we have how many orbitals? 5, right? So first electron will occupy 3D XY, second electron will occupy 3D XZ, third electron will occupy 3D YZ, fourth electron will occupy 3D into X square minus Y square, and the last fifth electron will occupy 3D Z square. So we need to draw upward arrow mark, one upward arrow mark in each of these d orbitals, which represents the positive spin. Now coming to iron, the atomic number of iron is 26. That is 1 electron is greater than manganese, right? So we have to follow the same method for iron as we have done for manganese. So 1s2, 2s2, 2p6 because it could accommodate 6 electrons. 3s2, 3p6, 4s2. Up to this, it is same as that of manganese. Coming to 3D orbital, let us see how much we have completed. 2 plus 2 plus 6, 10, 10 plus 2, 12 plus 6, 18 plus 2, up to 4s electron, we have completed 20 electrons, right? Here we have 26. So 26 minus 20, remaining how much are there? 6 electrons. So those 6 electrons will occupy 3D orbital. We know that d orbitals can accommodate the maximum of 10 electrons, right? Here we have only 6. So the electronic configuration of iron is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and 3d6 in terms of scientific notation. Coming to orbital diagram for iron, we have to draw the boxes as usual from 1s to 4s, and we have to draw upward and downward arrow mark which represents the opposite spins of electrons in each of this orbital. And finally, how many electrons are there in d orbital? 6 electrons. So according to Hund's rule of maximum multiplicity, the first electron will occupy 3dxy. The second electron won't pair up now. It will occupy 3dxz. Third electron will occupy 3dyz. Fourth electron will occupy 3dx square minus y square. Fifth electron will occupy 3dz square. Now all the orbitals are filled up, right? Now the sixth electron will occupy 3dxy orbital. Only the sixth electron will pair up with the first electron. In the same way, we have to draw the orbital diagram for cobalt and nickel, right? So how we have to write the electronic configuration? 1s, here also 1s, 2s, 2p, 3s, 3p, 4s. Up to this, the electronic configuration is same, right? Coming to 3D orbital, up to 3s, how many electrons we have completed? 20 electrons, right? But we have 27 in the case of cobalt and 28 in the case of nickel, right? So the remaining is 7 electrons. Those 7 electrons will occupy the 3d orbital in the case of cobalt, and the remaining 8 electrons in nickel will occupy 3d orbital. From 1s to 4s, we need to draw one box for each and every orbital, and each and every orbital we need to draw two arrow marks, one in the upward direction and one in the downward direction till 4s2. The difference is while drawing the orbital diagram for 3d, in the case of cobalt, how many electrons we have? 7. So first electron will go to 3xy, second electron will go to 3xz, third electron will go to 3dyz, fourth electron will go to 3dx square minus y square, and the fifth electron will go to 3dz square. Now all the orbitals are completed. So according to Hund's rule of maximum multiplicity, the sixth electron will pair up with the first electron present in 3dxy, and the seventh last electron will pair up with the second electron present in 3dxz. Understand? Likewise, while drawing the orbital diagram for nickel, the first electron will occupy 3dxy, second electron will occupy 3dxz, and the third electron in 3d will occupy 3dyz, fourth electron will occupy 3dx square minus y square, fifth electron will occupy 3dz square. Remaining 3 electrons are there, right? Now all the orbitals in 3d are filled up. So the sixth electron in the 3d will pair up with the first electron in 3dxy, and the seventh electron will pair up with 3dxz, and the last 8th electron will pair up with the third electron which is present in 3dyz. When you look at the electronic configuration here, we could see the 5 3d orbitals are progressively occupied. That is, in the case of manganese 3d5, in the case of iron 3d6, in the case of cobalt 3d7, in the case of nickel 3d8. Progressively, the electrons occupy the 3d orbitals. Like the electronic configuration of chromium, the electronic configuration of copper is also peculiar. So now we are going to see the exceptional electronic configuration of copper. Copper has the atomic number 29. That means it has 29 electrons, right? So to write the electronic configuration according to Happa principle, 1s, it can accommodate the maximum of 2 electrons. So 2. Then 2s, it can accommodate the maximum of 2 electrons. So 2 in the superscript. Then 2p, on the whole, it could accommodate the maximum of 6 electrons. So we need to write 2p and 6 in the superscript. Then 3s, it can accommodate the maximum of 2 electrons. And 3p, it could accommodate the maximum of 6 electrons. Then 4s, it could accommodate the maximum of 2 electrons. So up to 4s. Starting from 1s to 4s, how many electrons? 2 plus 2 plus 6 plus 2 plus 6 plus 2, 20 electrons, right? So up to 4s, we have completed 20 electrons. The actual number of electrons present in copper is 29. So 29 minus 20, how many remaining electrons are there? 9 electrons. So these 9 electrons will occupy the 3d orbital. This is the expected electronic configuration of copper, right? To draw the orbital diagram for this configuration, starting from 1s up to 4s, as usual, we need to draw as we have done for scandium, titanium and vanadium, right? We need to draw a box for each and every orbital, and we need to draw one upward and downward arrow mark which represents the opposite spins of electrons present in the orbit. This is the expected one, right? So how many electrons we have in d orbitals? 9. So we are expecting one electron to occupy 3dxy. Second electron will occupy 3dxz. Third electron will occupy 3dyz. And fourth electron will occupy 3dx square minus y square. And the fifth electron will occupy 3dz square. Once all the orbitals get occupied, now pairing will take place according to Hund's rule, right? So the sixth electron will come and pair with the first electron present in 3dxy, right? Then the seventh electron will pair up with 3dxz. So we have 2 electrons in 3dxy and 2 electrons in 3dxz. And the eighth electron will come and occupy 3dyz. So we have 2 electrons in 3dyz. And the ninth electron will come and occupy 3dx square minus y square. So we expect 2 electrons in 3dx square minus y square. This is the expected configuration, right? But it is entirely different from the actual configuration. Now let us see the actual configuration of copper atomic number 29. What is the actual configuration? Instead of 4s2 and 3d9, the actual configuration is 4s1 and 3d10. That is from 1s to 3p6, it is very normal. When coming to 4s orbital, instead of 2 electrons, only 1 electron will occupy the 4s orbital and the second electron goes to 3d orbital. So the actual configuration of copper will become 4s1 and 3d10. To write the orbital diagram for copper 29, so as usual from 1s to 3p6, we have to draw boxes for each orbital and we have to draw one upward and downward arrow mark in each of the orbital, which represents the opposite spins of electron in the orbit. While coming to 4s, only 1 electron will occupy. Instead of pairing up, the second electron will occupy the 3d orbital. When you look at these two orbital diagrams, you could see these d orbitals are partially filled. What is the maximum number of electrons d orbitals could accommodate? 10 electrons, right? Here, how many orbitals are there? 9. So it is not completely filled, it is partially filled. If you look at this diagram, orbital diagram, here, since 1 electron from 4s has shifted to d orbital, now these 3d orbitals are completely filled, that is fully filled. What is the maximum number of electrons that could be accommodated by s orbital? 2, right? Since it gives 1 electron to d orbital, it becomes half filled orbitals, right? So here also we have half filled and here also we have fully filled orbitals. So fully filled orbitals and half filled orbitals have found to have extra stability. So this electronic configuration have extra stability when compared to the expected configuration, right? So that's why this is the actual configuration for copper. As I said earlier, this reason can be well explained on the basis of the symmetrical distribution of electrons and exchange energy, which we are going to see in the next session. Now, students, you can please pause this video for 2 seconds and try to write the electronic configuration of the next element, zinc, with atomic number 30. I will show you the answer in the next slide. So this is the electronic configuration of zinc. It follows the same pattern as that of scandium, titanium, and vanadium. So 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and 3d10. Students, let's recall all the topics that we have discussed in this session. In this session, we have discussed the electronic configuration for the atoms with atomic number from 21 to 30. And we have discussed the exceptional configuration of chromium and the exceptional configuration of copper. Hope this session was very useful to you. See you soon in the next session. Have a nice day. Thank you.